Euclid's Postulate 5 has been one controversial candidate in the history of mathematics. Some of the great minds feel that even Euclid, the father of geometry, was not fully satisfied with the idea. To understand clearly, let's dive deep into and recall them all in a single breath or more than a breath. Let's go. The first postulate states that there is a unique line from one point to another, or a finite line that Euclid called as a terminated line and we call the same as a line segment, can be produced indefinitely on both the directions. The third postulate states that a circle can be drawn given a center and a radius. The fourth one says that all the right angles are equal. Now, let's come down to the worrisome postulate 5. Alright, so if you look into the Euclid's postulate 5, what it states is that if there is a straight line called as H crossing another two straight lines AB and CD, and some of the angles on the same side, in our case they are alpha and beta, if these angles they add up to less than 180 degrees or two right angles, then these lines are going to meet at some point on this side only. Right? So can we just try and see if the lines are meeting? Yes, they are meeting. Can I form a triangle using it? All right. Yes, so we form a triangle. Honestly speaking, when mathematicians were trying to prove the parallel postulate, it was realized that the parallel postulate itself was another version of the sum angle property, wherein I say all these angles they are adding up to less than, equal to 180 degrees. And in the process we discovered the alternate interior angles or the co-interior angles. And this is the way we prove the sum angle property of a triangle in our present day scenario, which in fact, or truthfully speaking, is just another version of the parallel postulate. The original proof to sum angle property can be found in my previous video, the way Euclid proved using congruent triangles. The next one is a snapshot from NCERT textbook for grade 9 that claims all efforts to prove the parallel postulate led to a great achievement that we today call as the non-Euclidean geometry. How it began was a bigger question. Let's have a close examination at Euclid's postulate 5. Pretty complicated. Let's go down to the visual proof. The visual proof states that if these two angles on this side are adding up to less than 180 degrees, the lines are converging this side, and obviously on the other side it is more than 180 degrees. Then there would probably be a case where these two angles they add up to exactly 180 degrees. That means you will have a line M which is parallel to the line G, and these angles are adding up to exactly 180 degrees. In the process to prove Euclid wrong, there were three scientists or three mathematicians who were associated, Gauss, Bolyai, and Lobachevsky. All three of them are working at the same time to prove the fifth postulate incorrect and taking us to the non-Euclidean geometry. They did this by two particular ways. One was case 1, when these two lines are parallel, right? They are parallel because some of the angles is 180 degrees, but they are not parallel because they are meeting at some points here. This was the spherical geometry. The second case that we observe is still difficult to realize. For that, I have created this as a small applet in GeoGebra that you can find it online. I'll just add on the link over there. So what we are trying to see is that we have to move these points such that they are not going to intersect my given line. Like in the previous case, these angles are 180 degrees, but the lines are not parallel. Every time we are trying to draw a line, it will not be parallel because it will always meet at the pole. In this case, I can draw infinite number of lines which are parallel to my yellow line, the pink line over here, sorry. So the pink line, I can draw infinite number of lines which will not be meeting this. So you can have infinite number of lines which are parallel, which are not meeting, not a single line, but infinite line. So the case one, I prove Euclid wrong by stating that there are no parallel lines because they are all meeting. The second way I prove Euclid wrong, stating that there are infinite number of parallel lines that I can draw to this line. One here, then you can have one here, and one here, and so on. There are many such lines. Now here I introduce the angle of parallelism. This is my angle of parallelism, which is a function of this distance in red, which is my h portion in the given figure. So you will have it as angle of parallelism. F of h is a function. You will have all the lines which are parallel to the given line in this portion, and these lines will never meet, and the other part you will see the lines which can meet. All the curves that I'm drawing in this portion, they will meet the given line. This is the ideology of angle of parallelism. Now as learners, we find it very easy to visualize a spherical geometry because we know a circle and we live on a sphere, but it's hard to imagine what we call as a hyperbolic geometry. Now giving it a view, we have asymptotic lines, and somewhere there we have angle of parallelism. So you'll have all the curves on one side which you will find, they're never meeting the given line, and then there are curves in a portion which will always meet my given line, right? So can you just try and imagine a hyperbolic geometry? And when I try to rotate it, I've just rotated my given figure such that my given line now becomes the vertical line. And can we just connect it to a Shivlinga? Can we just imagine it like a Shivlinga, the hyperbolic surface, or the saddle of a horse? Right? So not trying to relate it to my grandma's stories where I say that Earth is resting on a Shivlinga, so it's a combination of a non-Euclidean and a Euclidean surface. Nothing like that. But is it possible that the Earth can be resting on such kind of a figure? We are living on a non-Euclidean surface, and somewhere where the bumps we can see the Earth is resting over there probably. And then we have a pseudosphere. The question we are still left with, they are not answered as yet. They remain. Do we live in a Euclidean or a non-Euclidean world? Looking from outside, the world seems to be non-Euclidean, but inside we follow the Euclid's laws. That is to state, we live on surfaces which are locally Euclidean. Now this is what happened when Gauss tried to create a very, very big triangle just to prove the Euclid wrong, but he found that all the Euclid's laws were valid. He could reshape the figures. That means there was a concept of congruency, there was a concept of similarity, and the sum angles were all 180 degrees. Thereby we conclude that we live on a locally Euclidean surface, which is non-Euclidean from outside.